Uh, Thanks, Judith, and the rest of the Earth Science Department of the University of South California for organizing this Lithosphere Dynamics series. Today's presentation will focus on the Anthropocene aspect of the Lithosphere Dynamics, Anthropocene with an E and not an H, because we'll navigate through the concept of energy, entropy, mass balance. Basically, it's the Thermodynamics 101 applied to rocks with a twist, as we'll extend the journey to include some social, economical conclusions. Hence the subtitles, physical limits of natural resources extraction, Homo geologicus implication of meeting net zero. So I asked an AI to generate an image based on the subject of this talk, and a few iterations later, this is the AI takes on how we, humans, are influencing the state of the Earth crust these days. The result is a collage of a stereotypical cross-section of a tectonically active sedimentological sequence with bedding, folding, faulting. There's even what can be interpreted here, Artesian oil. There is even what can be interpreted as an artesian oil seep at the surface next to a structural discontinuity. Distributed underground are localized source of heat and pockets of magma. There is even a spot where the floor is lava. Obviously, some imitation of scientific article with legends here and there. In the background, the silhouette of skyscraper contrasting from the blue atmosphere. The biosphere is presented by bricks of greenery and what looks like a happy little tree Barbaros painted here to remind us that lithosphere is a substrate of life. Speaking of life, I want to quickly mention the late Lovelock that, among others, realized that Mars had to be dead because life needs to feed off a flow of energy in system far from equilibrium. And the current lack of tectonic activity means no gradient of any kind, and may be a reason there is no life on Earth, on Mars. Right, I don't know why it's not behaving the way I want it to. All right. So let's reach out on Earth instead and zoom into this map. It looks like some measles outbreak, but really it's all the mines and quarries mapped by US Geological Survey. That's our direct impact on the lithosphere. If I ask anyone here what mineral resources California is known for, you, the public of specialists, might mention Rio Tinto's Boron mine, which is indeed a world-class deposit. Alternatively, you may argue that Mountain Pass is the highest grade rare earth mine, and that would be correct. Here are the top 3 rare earth deposits currently known on the planet. And to give you a sense of scale on how your fractionated carbonatite compares with the others, I've taken these representation from Dreadnought Resources, exploration company here in WA that has had very good luck so far. And it's interesting to see how your sulfide queen deposit that produced 10.8 thousand tons of rare earth oxide last quarter doesn't share the similar carbonatite settings of concentric carats you find in Gwala in Tanzania or Mount Weld here down under. But we won't discuss these geochemical oddities for much longer, for when one is asked about what mineral resources make California the golden state, the answer is tautological. So let's start with the facts. The Clark of gold is an indication of its abundance in the Earth crust. It's around 1 part per billion with a B. So for 1 billion atom, 1 to 4 will be gold on average in the first 5 to 70 kilometers of the crust. So what miners call ore is this quantity enriched 1,000 times through geological processes. And such an anomaly is currently about economic to mine at 1 part per million. That is 1 gram of gold per dry ton one dry metric ton of rock. So gold is pretty much a needle in a haystack, and the value is really derived from the effort-intensive nature of its collecting. It's time-consuming for low-tech artisanal miners, and so it is for resource and it's equally resource and energy-intensive for the industrial miners. And it's only worth chasing if you've got not much better opportunity, really, and resources and energy are cheap. So this USGS graph shows how essential non-fuel minerals are to the US economy. But guess what? It's actually not the first limiting factor to generating $21 trillion of GDP. Energy is. And why do we keep forgetting about that? Because energy is so cheap, it's only making up 2% of our budget. And just because a couple percent of our spendings isn't much, we allocate a tiny fraction of our time to that issue. Yet, pretty much like your brain is 2% of your mass, you're 100% dead without it. So try making 98% of that GDP without the 2% energy to start with. Why is this so hard? It's so hard because energy is everywhere in the world we live in. And let's dive into that Thermodynamics 101 refresher. So energy is best defined as the ability to transform surroundings. Here, machines that lift, that carry, excavate, drill, push, grade, flatten, hold, tow. It's all about changing the original shape of the system. Mechanical energy is used to locally increase kinetic energy and potential stored energy from height. Mining gold is like any other human activity. It's just about changing the shape, height, spin, and carrying masses across space. And all of that involves energy. Any change in the chemical composition is a change of energy. You may be familiar with digesting your meal, casually recharging your phone, thirsty of electrons to turn lithium ion back into metal ions. It's no different in the mine site when you convert stored chemical energy in a blast. If you skillfully rearrange nucleons in a nucleus, you've got a change in energy levels, and the sun has been doing those thermonuclear reactions for the past 4.6 billion years. So really, energy quantifies the change of state of a system, and that's why it's so interesting, because you can see energy really everywhere. Any modification of pressure, temperature, shape, speed, chemical composition, atomic composition, entropy, enthalpy, energy, photons, modification of a position in the field, should it be magnetic, electric, or gravitational, everything is energy. And because energy is everywhere, means that we can count it and use it as a metric to perform a really accurate accounting of the world we interact in. And as long as the calculation is homogeneous, then we're all good. The other interesting thing is if the laws of physics can't be violated. You know all about the first law of thermodynamics, conservation of energy, delta E equals 0. Well, you can't find energy or make energy like that. You have to mobilize pre-existing energy already in the system environments and converting it. And then you're limited by those laws of physics and that Carnot yield based on the temperature of the hot source or the cold source. You know, whether you have a coal-fired power plant, a nuclear power plant, a geothermal power plant, it's all the same deal. It's all about that difference in temperature. And whether you decide by a vote in parliament that you're going to increase welfare or something, which is going to violate those laws of physics, you already can't. So there is no like things like that in Harry Potter making energy. So as energy becomes abundant, mankind transforms the world. And the more an environment was changed, the more energy was involved. By the way, that's the Kalgoorlie open pit, the Golden Mile in Australia. So let's introduce the concept of material footprint. So material footprint refers to the total amount of material extracted to meet final consumption demands. It is one indication of the pressures placed on the environment to support economic growth and to satisfy the material needs of the people. The global material footprint rose from a lot to a 70% since 2000, and as more can be seen on this graph. The rate of natural resource extraction has accelerated. So using the turn of the century as a reference, it's obvious that the global consumption of raw material increases faster than the GDP or the population on this graph from the UN. So in other words, at the global level, there has been no decoupling extracted in poorer countries. Those fancy tech gadgets at the Consumer Electronics Show are not going to make themselves. And what's the jigsaw part of the graph at the bottom here? Well, it's the estimation range of the annual sediment discharge by the rivers 4 to 22 billion tons. Basically, it's peanuts compared to what mankind is moving around. We, Homo sapiens sapiens, or shall I say Homo economicus, have become a source of mass transfer 5 to 23 times more significant than a naturally occurring erosion. Let that sink in. So surely you're familiar with that graph. I don't like it because it's not metric system, but you get the point. We've got a massive footprint. So even against the assuming 100 billion tons of natural movement happening nowadays, the contribution of extraterrestrial mass increase from the Earth is negligible. Hence a solid conclusion. We can consider our solar vessel to be a finite quantity, a stock given once for all, a closed system. We are, as a species, moving 62 million times more material than the external flux of elements reaching Earth through micrometeorites. And it makes sense. Once you remove the boron, mountain pass, and maybe an active gold mine, it's obvious that the bulk of what mankind digs from the lithosphere is mostly sands and pebble in quarries, gravel pit, plus marl, limestone, and clay for concrete production, so we can increase that urban sprawl. So when we're discussing energy, really all I want you to think about is machines. So historically, all we were able to do is consume primary energy in the form of biomass, and our body, a converter, managed to extract a bit of energy of that, make some fair work, a bit of work, and a bit of heat. And if we wanted more work be done, we needed either more converter in the form of animals or slaves, or an extra source of energy, like wood, for instance. And then we had to use other kind of converters to mobilize extra power. And basically, all we've done in the sense of history is finding more source of energy and more converter to use more machines. So where we are today, the average American is consuming 76,000 kilowatt hour per person and per year. And if you compare that with the amount of work Arnold is supposed to can physically deliver, 10 watt with his arms, 100 watt with his legs, 100 kilowatt a year, that's as if you had 766 slaves of Arnold's style working for you, crafting this computer, that chair you're sitting on, this clothes, and that's the world we live in. We are in a world of abundant energy. And does that mean teamwork does a dream work? Well, let's discuss the story of Totos in Africa, Madagascar, in that sapphire mine. So both cubes of gem-bearing dirt and water need to be removed from that open pit. So you've got a choice. Either you go full artisanal, or you may get some assistance from the fossil fuel. So mind you that Malagasy Schwarzenegger is an average salary here, that is $500 US a year, and he can deliver 100 kilowatts of labor annually. So that's a basic E equals mgh that applies here. So trivially, you conclude that the price of the human-powered kilowatt hour is 50 cents. That would be $54 for that same kilowatt hour if you're using an average American worker. And then the gasoline is trading around 5.2 US dollar per gallon in Madagascar now. That's it's in LA, it's around 460 to 560, whether you go gas or diesel. Say 5 for to even this out. So what do you get for this? Every time you go to the petrol buzzer to fill your massive tank, there is a content in each and every 1 liter of petrol, 10 kilowatts hour of primary energy. You want to recover this energy that bonds the carbon and octane together. So you then feed this refined black gold into your favorite converter, a thermal engine, with a thermodynamically constrained yield, remember Carnot, around 20 to 40% in practice, which turn your 10 kilowatt hour of primary energy into 2 to 4 kilowatt hour of usable mechanical work to power a pump for dewatering, for instance. How lovely! Let's make the kilowatt hour of final usable energy or mechanical power of fossil fuel worth around 40 cents. So here in California, if you are to plug yourself to energy to the grid, get electricity, is going to be 30 cents a kilowatt hour. So on one hand, you've got fossil fuel that works 24/24, doesn't require leave or social rights, is easily transportable and storable in the form of gasoline, and costs 40 cents a kilowatt hour. On the other hand, human labor costs anywhere between 50 cents and $54 a kilowatt hour, depending on where you source your workforce. What do you choose? Well, the answer is in the picture. Why are they not dewatering with buckets? They're using a pump. It's cheaper. Why did we stop slavery? Is it because we started to care about ethics? No, it's not. Because even if your slave is costing us $500 a year, it's cheaper for you to use a machine instead, even with a terrible yield. So this is what energy has given us, the ability to trigger modern mining, whether you use that XRF gun that's going to require 5 watts, or a laborer, 100 watt, lighting tower, 60 cyclists pedaling, that Ford Land Cruiser, whatever, that's the power of 15,000 cyclists, 1,500 cyclists, sorry. A drill rig equivalent to 25,000 pair of arms hammering down those rocks, you know. An excavator, 81,000 pair of arms. A dump truck that's got the power 10,000 times the pair of legs of its driver. A mill to crush rocks, 600,000 pair of arms. Maybe you're familiar with US-based Alcoa alumina plants. They consume down here around 90 megawatt of electricity. That's equivalent to 90 million pair of arms. It's 4 times the population in Western Australia to hammer those sheets down. So this is what energy has enabled us. Massive impact. And you could even go further and maybe one step too soon, discussing the relationship with the 32 petajoules that just got released in a recent earthquake. But who am I to lecture you about this when you've got the San Andreas fault in your backyard? So this is energy, is the ability to transform surroundings and to build a more complex, more powerful exoskeleton so that our desires of dominating and curbing nature can be met. Progress has enabled the bipeds that we are to effectively multiply our power on nature by numbers and orders of magnitudes. The operator of the dozer can now clear the bush at a pace of an army of 68,000 people by sitting in the cabin with cooling aircon. And to some degree, it doesn't really matter if that engine is being fueled by coal, diesel, gas, electric battery, or even worse idea, hydrogen, because the end result is the same. You can clear the entire bush or rainforest with a dozer running on green, brown, black, blue energy. So it's more about what do we use this energy for? And globally, as a species, we still love fossil fuel very much. It's 82% of what we are consuming. And you can see that only the tiny, tiny top there gets reported by the media, really, when 82% of the discussion realistically should be about fossil fuels. And in the US, it's no different. You can see that from 1960 to 2008, oh, why 2008? I wonder, was growing and then past the peak, and it's on the decline, and you're using slightly more fossil fuel than the rest of the different places. So say that the target was to be 100% renewable. I guess we are a few studies short of a 6-pack in that regard, given the current rate we're doing. And why is it so hard again? Because energy is everywhere. Iron and steel mining and refining, plus that of the non-ferrous material, accounts for 8% of the energy, of which half is dedicated to grinding and crushing those rocks. So combination is super energy intensive, and 4% of the global energy is being spent on crushing those rocks down, which is the main expense on a mine site before excavation, hauling, drill, blasting, conveying the ore, or doing some disposal of tails, flotation, or leach, depending on your process. So really spending a lot of time and efforts and energy on grinding and crushing. So a bit of math now. There is a version of the mean value theorem that states that, among others, an infinite growth in a finite world can't happen. Even if you're an economist or a politician, the math go against it. So if you consider stock given for once, and there are X tons of a given metal on the planet and no more, makes a finite quantity, right? And the yearly extraction rate can't increase forever. It can't remain constant forever, otherwise you would have an infinite stock. So in a world with limits, like we are, with zero expansion at plus and minus infinity, you have locally to go for a peak, regardless of the shape of that peak. And it seems that we've passed that maximum. So basically, long-term sustainable green growth and is one of the many hilarious jokes you can tell yourself. So this is something that received little coverage. In 2008, the World Energy Outlook, 2018, the World Energy Outlook had that tiny sentence here saying global conventional crude oil production peaked in 2008 and has since fallen by a few million barrels a day. Is this linked to the financial crisis? I'll let you guess so. So in the 2021 version of the World Energy Outlook, oil demand projection, not production, shows for the first time an eventual decline in all the scenarios, the steps we're doing and where we should be going in terms of net zero. And as Simon's cats know better than us all, these machines require their own kind of pet food, and it's definitely going to become a problem if we can't change our diet. The 2022 World Energy Outlook becomes the first scenario that sees global demand for each of the fossil fuel, oil, gas, and coal, exhibit a plateau or past peak. So coal demand peaks within the next few years, natural gas demand reaches a plateau by the end of the decade, and oil demand reaches a high point in the mid-2030s before falling. And the result is that demand for fossil fuel declines steadily from the mid-2020s, that is now, by around 2 hexajoules, that is 1 million barrels of oil equivalent per day. So the peak is behind us. And what does it mean when COVID is not around? Well, the main limiting factor of the economy is actually the oil and gas in the ground. You can see those two graphs are very much correlated, but one is driving the other. And actually that is first a dip in the oil consumption, and then you got the dip in the GDP per capita. I would actually highly suggest reading this comic book, A World Without Hands, and I've borrowed a few slides from that to illustrate that point. So thanks to the discovery of oil in Pennsylvania, Vanity Fair in 1861 reported that it saved the whales, and actually it's pretty on point. So there are some good benefits of oil and gas, I guess. So oil and gas prospecting really is all about Easter egg hunting, as in you find the biggest, least well-hidden one first, and then you're going to have for the trickier one, the deeper to oil, shale oil sands, fracking, all the more complex stuff. And then you can ask yourself, is it behaving the way we economists describe that with the regular models? Actually, not quite, because when you dig, you realize that in 2004, big oil invested 70 billion to extract 17 billion barrels per year. Fast forward a decade, with 300 billion, so a lot more, the amount of barrels recovered was significantly less. So the hallmark of oil scarcity isn't actually in the price, but it's rather in the amount of investments required to extract it. And nowadays, what's happening is just trying to limit the decline. And another good indicator is that energy return on energy invested. So you might ask the question, is it explorer's end game? So on the left-hand side, you've got here the theoretical behavior between the price and the volume for any good. That's what the economists would like to see. But on the right-hand side, what you have here is what we actually see when we're plotting the graphs. So let's dig a bit deeper into that. So this is the textbook example of elasticity, that is the price-volume relationship with Australian diamonds. And it looks like a mint curve, as if there was a diamond cartel controlling the invisible hand of the market. But let's plot oil at the global scale instead. And what you can see here is from 1965 to 1972, increase in quantity consumed and produced, not increase in price. Then you've got an increase in price, not in production, and then production not in price, and then price and not production, and then drop in production in price, but not in production, and then goes up. Basically, there is nothing like that straight concave curve we saw before. It's like that erratic trajectory of a balloon that has been here adjusted for inflation using 2021 constant dollars. And if you're using US data instead, it's the very same unbehaved merry-go-round trajectory, and looks like a balloon again until the head of state wants it to pop and make it a bit different. And this is the same with gas in the US, not a single straight linear behavior or nice curve until the head of state wants it to pop again. You can see the influence of fracking in the more recent years that have enabled more quantity of gas to being generated and price capping. If you're using gold as a comparison here in Australia, you can have decreasing quantity, increasing price, increasing quantity, decreasing quantity, increasing price. There is not always a good relationship. So just because it's cheap doesn't mean you're going to have a lot in the future. So last year, well, actually the year before, in 2021, globally, we increased coal consumption by 6%. That is an extra 6.4 billion tons of coal a year, which makes you question, have we actually learned from this Kiwi newspaper from 110 years ago that said that burning coal makes the air more effective blanket for the earth and raise temperature? The effect may be considerable in a few centuries. That's now. So yeah, I don't see this curve slowing down but anytime soon, and this is the CO2 emissions. So breaking news, carbon dioxide is an oxide, and pretty much like quartz, corundum, spinel, magnetite, rutile, cassiterite, they have a very strong oxygen bond, making them resist chemical attack, and that's why you accumulate these minerals in heavy sands. And CO2 is just the same, it's very hard to break apart. So I let you pick your most important figure here, that is the atmospheric content. And for that, I've got a really nice video here. So there were 280 ppm of CO2 in the atmosphere at the time of your founding father, up to 307 when your favorite geologist president arrived in power. And it's only gone up since, up to 420 ppm today. You'll find this is a very robust trend with numerous data points throughout the globe. Thanks to Mr. Kelling, who started recording in 1958 in Hawaii, the red dot in the graph, and NOAA and the other organization for keep collecting and presenting that data. So carbon is continuously exchanged among the reservoirs through natural processes that occur at different various range, from daily to seasonal fluctuation, and to very long-term cycles which occur over hundreds of millions of years. For example, there is a clear seasonal cycle of atmospheric CO2 as plants photosynthesize during the growing season, removing large amounts of CO2. Respiration and decomposition of leaves and organic matter release the CO2 back into the atmosphere. On the scale spanning decades to centuries, CO2 levels gradually fluctuate between the ocean and the atmospheric reservoirs. There is a partial pressure equilibrium between the air at the surface of the water and the water in contact with the atmosphere, which means that should the CO2 concentration start decreasing in the atmosphere, the sink that the ocean is will re-equilibrate by releasing the excess CO2 that was dissolved. And due to the large surface area of the ocean and the high solubility of carbon dioxide in water, the ocean stores a very large amount of carbon. That's 50 times more than what the atmosphere and terrestrial biosphere. Much longer cycles can also occur on the scale of geological times due to the decomposition and weathering of silicates, mafic rocks, and carbonate rocks. To determine if the phenomenon is part of the statistical noise or significant, it's always a good idea to look for the longest available data set. This way you can grasp the scale of the given variation. And here, this graph is worth 1,000 words. The last time the planet was at 420 parts per million was when Homo habilis was leaving Africa 2.5 million years ago. You're allowed to cry. It's always a shame that sometimes we got good news and bad timing with social media and regular media preferring to the coverage of billionaires' big dick energy in a space battle rather than covering the IPCC report release. And everyone here in the audience today is making decision, and they've done a 42-page summary for decision makers. Please read it. In case you haven't, here is an extract. And that's a graph from that report, and don't be surprised if you don't see the contribution of carbonaceous chondrites to the overall energy budget, because it's pretty negligible. So from 1750 to 1850, there isn't much human impact on the radiative forcing. That is the difference between the energy that reaches the Earth and that is radiated away. It changes when we start emitting significant infrared absorbing greenhouse gases. And while the fine particles of aerosols have a cooling effect, it's not enough to counteract that extra blanket provided by the greenhouse gases. Even the minute particles generated by the volcanic eruption, you can see these peaks here, is not enough to prevent the sun from reaching the Earth too much. And as consequences, overall, we've got an added 2.8 watts per square meter of radiative forcing. So really all we do is burn now and pay later. Here's a graph from the 5th IPCC report showing a response of an idealized instantaneous CO2 pulse in the atmosphere. It takes 100 years for plants to remove 60% of what was injected. If you see, by 10,000 years, you only remove 90% of what you put in. So by that time, you're dead, I'm dead, any government is history, the 2020 kids are dead. So there is really no longer term incentive for action, which is, well, we're lucky that Egyptians didn't build their pyramids using fossil fuel. We would otherwise still have their CO2 around today. So the conclusion of this is that if this is the hottest summer in your life, well, it's so far. So because you can tell your kids the climate you enjoy is now lost forever because of the inertia of the system. And you're emitting in the US around 16 tons of CO2 on average a year, and it's far too much. You'll see why. So let's have a look at what's on the menu. You've got direct proportionality between cumulative CO2 emissions and temperature. So basically, if you consider past emissions of 2,390 gigatons of CO2 from 1850 to 2019, and you want to keep emitting, then you've got different options. Either you want that 1.5 degrees, so direct reading of the graph, you've got another 500 gigatons of CO2 to emit. Maybe you want to get 2 degrees instead. Well, you've got a budget of 13,000 gigatons of CO2 to emit. And if you divide that evenly between the 8 billion inhabitants on Earth, that makes for a personal carbon budget of around 2 tons per earthing. So it's record compared to the 16 tons on average for Americans. So that means in practice, you're going to have to divide by 3 the current MLNG and the current greenhouse gases we're emitting. That's what it means to be on target, and not even for the 1.5, it's gone for the 2 degrees. So dividing by 3, what does that mean in practice? Well, you're maybe familiar with the composed interest. That's pretty much the same. So you want to divide by 2/3, so have 1/3 of the total. You've got 28 years till 2050, so that's going to be a 4% decrease per annum. 4% decrease per annum is what happened globally in 2020 because of COVID. So if we want to meet target for the next 28 years, you need an extra COVID on top on the shutdowns pre-existing, the lockdown, sorry, pre-existing, every single year till 2050. That's what it means globally to meet targets. And the thing is, if you snooze, you lose, because the journey is about the destination, and the earlier we start, the better off we are, and we should have started a long time ago. And why does that matter? Well, this was America 10,000 years ago. So there was a 3-kilometer thick ice cap on Canada. It was much easier for you to win hockey then. And as a result, the water had to come from somewhere. So the ocean was 120 meters lower. And then fast forward 10,000 years, we are globally 5 degrees warmer. And this is the US you know today. In Europe, you could cross between France and the UK. There wouldn't have been no Brexit. There was no water. But this happened in 10,000 years. We are on track to doing this in the next 100 years or so. Is it going to take place at the same pace with the same consequences? Maybe not. And that's another interesting graph. We're showing the average daily number of days in a year where the humidity is above 100%, so saturation of moisture, and the temperature is above 35 degrees, that is the temperature of your skin. So basically, you can't perspirate, you can't thermoregulate, and if you're a warm-blooded animal or human, you die. So these people in this area here are most likely going to be willing to go in places where you got aircon or flood country. And obviously, is that going to happen peacefully? That's a big question. That's another good joke. We got good comedian in the US. So let's discuss Kaya's equation and start with tautology CO2 equals CO2. And let's have some fun by multiplying the right number of the equation by 1, or actually multiplying and dividing by another term, the total energy supply in the world. So we've got this. So we've introduced a term here that appears at the ratio of CO2 over energy. That's the quantity of CO2 emitted per unit of energy or transformation of the world. So remember, energy is that physical modification of your surroundings. This term is hosting all the debate on decarbonization, ditching out fossil fuel, replacing wind by nuclear, hydro, solar, wind, biomass, and so on. So if you redo the straight with GDP, now you've got another term that is showing you how much energy you need to have as an input to create $1 of added value, all right? And then you can go one step further by multiplying and dividing by the population. So now the new term here, GDP per pop, is GDP per capita, how rich you are, but also how much services do you have available for the population, and then time the population. So one direct consequences of this is that, well, the CO2 emission are a linear function of the size of the population, right? So all things being equal, the more, the merrier, the more, the greater the emissions. Conclusion number 2, CO2 emissions are proportional to production per capita. So that is, society can have infinitely growing food and services, ever increasing purchasing power, while the CO2 emission drop, while a decoupling only happens if the other terms of the equation are balancing out. Third conclusion, reducing CO2 emission is proportional to the efforts of driving down the energy requirements of our productive economy. This term improves only if you're using less kilowatt hour to mine the same amount of gold, for instance. So this one is technology driven, unlike the others. And at last, we discussed already the substitution of the source of energy. So if you want this side of the equation here to be divided by 3 by 2050, that means this side of the equation has to be divided by 3. So how do you achieve that? Well, you can go Thanos style and say, well, let's divide the population by 2/3. The problem with that, and it's not going to happen because even wars and famines are are not quick enough to drop the population, and every loss of human life is terrible, but even World War I, World War II, or the numbers of COVID are not matching up. It only takes 1 year to 1 month to cancel out all the death related to COVID. So with 1.1% growth per year of the global population, by 2050, it's going to be up 29%. So we have to forget about that. Option 2, decarbonize your energy. Well, the problem is the data indicates only 20% efficiency was gained in the last 50 years. So at the current rate, it will take 3 centuries to reach net zero emissions, and we just don't have time for that. So how do we do? Well, maybe we have a look at the graph. So the US here in red, and you've the US has seen a stronger decline in CO2 intensity post 2008, following 50 years of slower reduction than the rest of the world. So there is a really good website called Electricity Maps that I would highly advise you to have a look at. So on average in California, you are at around 0.444 tons of CO2 per megawatt hour. Obviously, it depends from the day, how much sun you're getting, and so on. But this is a very interesting map, interactive, where you see how the grid is interconnected and which counties are doing a bit better than others, and globally, how much worse you are than other places like Canada. So let's move on. So option 3, you can decrease the reliance of GDP on energy. So the economics call that decoupling. Techno solutions are saying it's going to happen. Government are saying it's possible. Sadly, it's pretty much an illusion. The only realistic economic growth that doesn't require energy is when inflation introduces value, and there is not backed by a physical change in the real world. So take the capital gain tax or on some land or property, there is no intrinsic energy requirement for that, and yet it's delivering financial value. It drives speculative bubble and never lasts. So if technological progress has reduced the energy requirements of production of goods a bit, it's not the main driver to this graph. And the answer lies in the recent growth of the service business and the rest of the tertiary sector. Is the dollars coming from the realtors selling houses to miners needing accountant educated by teachers, protected by insurers, etc. That is making the whole system very reliant on the primary sector. And so those minus 26% of efficiency gain in the last 28 years have been great, but not enough. And so we eventually have to look at another option. So this is the best macroeconomic representation of the world. It's a very straight line, slightly concave, and that shows that the world tends to require a bit less energy to generate economic value, but it's not obvious that we're decoupling by moving on the right, creating monetary value without consuming more energy or the same. So nearly all the efficiency gains are lost in the rebound effect or take-back effect. The car require less fuel to travel the same distance, while you add more safety, more weight, and you go further for the next holidays. So you should have understood by now that energy is not just a cog in the wheel of our modern economies, it's the wheel itself. And you can name any impact there, except for COVID. We've never gone down that track, regardless of what we've done on the global basis. So last option, if you need that side of the equation to balance with all of these, overall, you're only down 7% here. So you need the production per person to decrease by 60% to catch up. Is it realistic to get that to bear the entire weight drop? Well, in the time it lasts, in the last 28 years, which is nearly the same of what we've got left by 2050, the wealth by inhabitant has risen by 58%. So that's how you are able to buy food which isn't produced locally and is coming from an exotic location. That's how you finance long studies, and you come to University of South California to do long studies. That's how you can afford not working weekends or even retiring. So there were not too many spare mouths a couple of centuries ago, and basically we have to revert down that curve if we want this to match. So the last option is that of mixed degrowth, that is going back to levels of 1966. That's the only way you can drop by 3 the CO2 emissions, and similarly, you have to drop the GDP. So that means giving away 60% of your salary, basically. So I hope now that you enjoy that best representation of the world, that is both primary energy and CO2 emissions are linked to GDP, and if you want to go down, the GDP has to go down too. That there is no such thing as decoupling on a macro scale. So a bit more about the galactic limits to growth. Global primary energy demand increased by 5.8% in 2021. So understand more GDP, more money in your pension fund at a pace which you hope is going to remain constant till you retire. But let's be super conservative and assume a 2% growth instead, all right? Math geometric suits say that 2% composited growth means doubling every 37 years, whether you're on Earth or in a galaxy far, far away. So the energy reaching Earth is currently 7.5 thousand times more than what we mobilize. And you can quote your favorite techno solutionist idol like Bezos or Musk that says that it's equivalent to having the whole of Nevada being covered with solar panel. Well, in 37 years, we need another Nevada and another one. And 450 years later, you require the entire whole Earth to be covered in solar PV to meet your ever-growing energy requirement. And then the billionaires extract themselves from the planetary limits and offer to colonize space. All right, let's go there. Well, 2% per annum return requires you to use the whole sun energy 1,500 years later. And then another 37 years later, you need another sun, Proxima Centauri, 4 billion light years away. If you want to be there in time, you're going to have to travel past the speed of light. Good luck breaking the laws of physics. In other words, pension funds, BlackRock, Vanguard, and others won't be able to deliver 2% yearly return infinitely, or even any positive return. Otherwise, in 1,000 years, you'll get 400 million more than what you started with, and physics won't let you have that. So critical minerals are a fundamental part of the energy and electricity security landscape. Demand for critical minerals for clean energy technology is set to rise 2 to 4-fold by 2030, depending on the scenario, and as a result of expanding deployment of renewables. So copper sees the largest increase in terms of absolute volumes, with current demand around 6 million tons per annum, and increasing to 16 million tons in a net zero emission scenario. And remember, just because you've got cheap price at the moment, it doesn't guarantee volume in the future. And it happens that production has to stop because of climate-related issues. I'm going to have to skip on the carbon price, but just so you know, some study mentioning that $100,000 per ton instead of a couple 75 euros, for instance, is actually the real price of carbon we should pay because of the consequences of that. And then the other problem of this talk, for instance, is that there's that carbon tunneling where we don't focus on how the nitrogen and phosphorus cycle are being disturbed, or the freshwater withdrawal or non-conversion, biodiversity loss, air pollution, and so on. Get the picture. But let's keep going on CO2 because, well, it's easy to discuss. I assemble a bit of data from the gold players, and it's quite convenient because it's so much easier to collect information from gold miners rather than other oligopolistic metallic commodities. You've got 500 companies producing gold, 850 plus mines. They report on the greenhouse gas emission, most of them, mostly on the scope and one, missing on the third one, but it's still better than nothing. So here is the graph. So you can see that is America first? Not quite. USA is at the bottom of the top half. and it's not harder to be better than South Africa using brown coal to power 3-kilometer deep mines, using up to 5.2 tons of CO2 per ounce. So at the opposite of the spectrum, you've got the fully electrified Makassar gold mine in Canada with the lowest greenhouse gases emissions of 53 kilograms of CO2 per ounce. So the good old trick of the trade is to try to report emissions per ton rather than per ounce, but the public is no fool. There's a reason the all-in sustaining cost is reported per ounce in financial reports. It's because that's what the investors want to look at first, because the metrics are based on ounces, not tons. So grades are globally declining and emissions are increasing over time, and underground typically requires higher grades to be economic, and their lower strip ratio means that they're going to have a lower CO2 footprint per ounce too. Well, there's something about that carbon risk, as in it's got financial and value implication. Some pension, sovereign, for-profit fund might look at this as a ESG criteria and maybe consider there's a potential for green premium. How is your mind going to be affected by a rising carbon price? It's easier to borrow money if you can prove that you won't become a stranded asset. So that's a simulation of what would happen to the price per ounce if there was a 100-ton increase in the CO2 price. Not much of an impact, really. So Equinox Gold, the company you've got here in California, isn't doing too bad, actually, because they're using heap leaching at this Mesquite and Castle Mountain projects. Core Mining hasn't any available data because, like Providence Gold Mine, they're not active mine sites. And the Rise Gold project, fourth player here, is assuming 0.06% ton of CO2 per ounce of gold. And if you look at this graph, it just doesn't make sense. Like, I'm looking forward to seeing in their project how they're going to manage that in that Idaho, Maryland mine, because it seems pretty unrealistic to me. So what have we done in history? We've tried to turn black gold into gold, or anything really. Historically, it's shown that with an infinite quantity of energy, any granite can become a source of aluminium. You know, you can even mine gold from seawater. You can do anything once you have energy. Fancy mining some ore at a few percent per ton, we'll find it. A few grams per ton, we'll find it. A couple carat per 100 tons, we'll find that, as long as we don't have to be behind the shower. So the very same can be done with CO2 equivalent emission than what I'm going to produce here, but I leave that to the audience as a trivial exercise. So once you've got energy, basically you can get as much copper or lithium or rare earth as you want. So these are figures taken from like Sunfire with 90 gigajoules of energy. You can get a ton of copper and bonus gold. 36 gigajoule of energy, you can get a ton of lithium plus some niobium and tantalum in the concentrate as a bonus. 23 gigajoule of energy, you get a ton of rare earth oxide. And if you want that process, that's going to cost you 76 gigajoules. If you want a nickel, copper, cobalt concentrate, that's 31 gigajoule based on IGO's number. But compare that with gold, it's like 10,000 times more intensive because of the grade. And look for diamonds, even 100 times more intensive for those diamonds. So makes you question, towards which commodities should we focus our efforts and allocate our energy expenses? Breaking news, it takes lead and graphite and sulfuric acid to make car batteries. It takes lithium and nickel and graphite and cobalt and other metals to make other kinds of batteries. And the more recent the technology, the more miniaturized, the more dispersed the elements are. You've got $2 of metals worth in that smartphone. How are you going to dismantle this for a profit by hand to scavenge that tantalum from the condensators rather than mine more columbite? You're just not going to do it. And here in the Scientific American, making the entire US car fleet electric could cause lithium shortages. Oh, no jokes. So here you have comparative analysis of the metal content of two cars, but you don't need 200 kilograms of critical material if you're driving a bike instead. So Is mass balance a recent problem? Well, maybe a hearing in Senate will fix it. Actually, no. Where are these elements going to come from? New mines, bigger holes in the lithosphere, more dispersion, and naturally occurring geochem anomaly? For us to meet net zero scenario, the damage surge by 2050 is expected to increase 26-fold for lithium, 6-fold for cobalt, 12-fold for nickel, and 9-fold for graphite. Where is this going to come from? So this basically tells you how much of a bottleneck these elements will be if we want to meet targets by 2040 this time. Choose your source in this prognostic for the highest return in the coming decade. So whence do these minerals will end up? Ranked number 1, grid for the electricity distribution. Rio Tinto's Bingham Canyon porphyry, better keep getting that copper out of the ground. Number 2, wind. You'd better keep producing at your mountain pass those rare earth for the magnets. Number 3, solar PV. You'll net a fair bit of copper, silicon, silver, tellurium, zinc, and other critical minerals for that. So what is going to balance out the growth of these critical minerals? Well, that's going to be the degrowth of coal mining, as we're expecting to be better off overall. Yes, for the better, money-wise. And critical minerals extraction is geographically concentrated, with a single country accounting for over half of the global production of several key minerals, notably graphite, China 79%, cobalt, DRC 70%, rare earth elements, China 60%, and lithium, Australia 55%. And to some extent, it doesn't matter from which place on Earth whence the ore is procured, for it's most likely to be refined in China. Governments are becoming increasingly aware of this sovereign risk. And then you can go beyond Kaya's equation, starting with, again, tautology, that metal is strictly equal to itself, and so is energy. Any metal is just some energy spent, as we've seen, and that energy is being itself more or less metal intensive. Like in Minecraft, mankind started with some wooden stone tools and later developed increasingly complex metallurgy. A metal-free wooden pan is enough to collect some gold powered by a metal-free human. You end up with a net positive metal gain. Honest job, but ain't much. You upgrade for a metallic spade and shovel and a sieve and maybe some mercury. The rest is still human labor. And so you up your game again with a piece of technology called a metal detector made of metal in the coils and batteries, and then you trade your horse for a 4x4, not to carry your gear, but you want to enforce your social status, you know? And then while finding more yellow metal. And then you buy a dredge and pumps and shaking table that are all electricity powered. How metal intensive is this energy going to be? So this is how much metal you need per kilogram, in kilogram per megawatt for different energy generation solutions. And while the fossil power generation, while the fossil power station require little metals, and the next least metal intensive is a nuclear power plant, better than solar and wind. And these metals mined with fossil fuel to date can then be used to generate renewable power used in a mine site to extract more metals. But does all of this add up together? Well, by the time you realize that you need a fair bit of the periodic table element for just those nuggets of plain gold, and it's even greater reliance if you take it into the industrial stage, you know, mankind is trying hard to locally increase the metallic content of energy because it's more comfortable to have fossil fuel and electrons thirsty machines built with metals to do the job for us. Yet, we subsequently depleting stocks of locally enriched geological anomalies, which means we're spending an ever increasing amount of energy for metal yield, which is not catching up. If we want the system to remain at the equilibrium within the physical boundaries and constraint of the planet, this identity here can't drift away from one in the long run. Regardless of how energy intensive the process is it a wise allocation of resources to lock so much lithium, nickel, copper, rare earth, and so on for the mining of gold? Or should these metals better be used in prospecting and mining of commodities relevant to the global energy transition challenges? This is, in my opinion, what it means to respect the planetary limits of the lithosphere while being in line with the long-term net zero goal. So what's gold? Well, the question matters because gold is not just made of 79 electrons spinning around the nucleus. It's about the energy of a star that dies, the energy of the miners and the machine they use. It's about the effort and the length of time mankind spends in the search of this desired yellow metal. Energy over time is the physical definition of power, not just the power-intensive fight against entropy and dispersed load rate, nor power through domination by wealth, obviously, but the power to say no, the power to understand that just because we can doesn't mean we should. Californians have the power to decide what legacy they want the Golden State to be for the next generation. How can you make a lasting impact for the centuries ahead? Will the gift of a piece of recycled lithosphere brought to the surface in a very dynamic event do the trick? If it becomes obvious that the logical goals are out of reach, don't change the goals, change the action steps. Thank you.